Agents and Task Management by Group C. Written by Manuel Alejandro Umaña Rodriguez, Dahyna Martínez Pérez, Jean-Louis PEREZ-DEJESUS, and Christopher Hans Mayens Matías. The agenda includes purpose of experiment, hypothesis, concepts, experiment setup, information, conclusion, and credits and references. Purpose of experiment. The purpose is to investigate the agents in different kinds of environments to better comprehend the functionality of agents in artificial intelligence practices, and to study the performance and efficiency of different agents in various environments, both with and without memory. Key questions and hypotheses. The key question is, does the memory of a reflex agent affect its performance and efficiency? Hypothesis. Since a reflex agent only knows its current state, adding memory will provide context, reducing errors and improving performance. Concepts. The platform used was Python. The subject is the agent's ability to clean an unknown environment, and the measure is the agent's performance and effectiveness in cleaning the environment within the fewest moves.
Experiment setup. The tools used for this experiment were the IMA code repository, which is the base repository these problems are taken from. For problem 2.11, the vacuum_agent.py was used, and for problem 2.14, the xy_vacuum_environment.py was used. The methods for comparing used were performance, which is the measure of how well the agent makes the steps to achieve the goal, and efficiency, which is the percentage use of resources for the agent performing its task. In 2.14, the same criteria was used, but for 3 different cases, which would be reflex agent with randomness in complex environments, reflex agents with randomness with no memory state, and with memory state. For exercise 2.11, the graphs were created by gathering the performance and efficiency of each state of the vacuum cleaner within the environment. For performance, we added 10 when the agent cleans a dirty block, and subtract 1 when the agent moves and does not reach the goal state. For efficiency, it was the number of dirt that has been sucked divided by the number of steps required to complete the task. This was the same for 2.14, except instead of adding 10, we added 100, and we also had a specific limit of moves because there was a chance that the agent would infinitely continue to move around the canvas and not finish its task. Information. For the simple 1x2 vacuum environment, these were the cases, which are the possible states for a vacuum cleaner environment of 2 boxes. Here we can see all the values obtained in the table, but we're going to move on to the graphs to have like a better viewpoint. For graph 1, you can see that depending on where the agent, or in this case the vacuum, starts, is going to have way better performance or way worse performance. It always depends on if it's close to the dirt block or if it has a clear path for it. And the efficiency basically showed the same result, but we have a more numerical value, percentage value, that tells us exactly what's happening in each state.
Information of the states for simple XY vacuum environments. In the next few slides, we're going to be showing you the different experiments and the results of said experiments following these slides. The biggest offset that was created in these experiments is in the case for figure 5, where the no state environment actually completed the maze for one experiment, while with the state did not even complete any single one, creating timeout for every single test made. The reason for this is that the traceback that was being created, so that it avoided spaces that it had already cleaned, was making it so that it got stuck in different corners of the environment, being unable to continue or move out of said corner.
Conclusions and lessons learned. Impact of partial observability. Limited environmental awareness requires the agent to balance movement and verification to ensure efficient cleaning. Action efficiency and initial state dependence. The number of actions required to reach its goal depends on the agent's starting position, affecting overall performance and effectiveness. This was seen in problem 2.11. Memory's role in agent performance. An agent with memory can significantly improve by avoiding revisiting already cleaned areas unnecessarily. Impact of randomness on efficiency. The random movement of the agent significantly reduced efficiency, often causing it to waste cycles by bumping into obstacles or idling instead of following an optimal cleaning path. Strengths and weaknesses of the state-based agent. The state-based agent performs better in environments with movement-limiting obstacles by avoiding repeated mistakes, but its memory constraints can trap it in a loop or hinder coverage in larger areas. Constraints of the reflex agent. A reflex agent is limited in complex environments because it can only react to its immediate surroundings and lacks the ability to plan efficient movements. Now the credits and references. These were our references.